Good morning, everyone. My name is Ashis, and I bring 23 years of experience in IT, specializing in data engineering, building real-time, near real-time applications in business intelligence, data warehousing, other applications. Currently, I'm employed with MasterCard as data architect. Throughout my career, I have designed and implemented complex data solutions for major organizations across the industries, including British Telecom, Barclays, and many other Fortune 500 companies. My main expertise lies in creating scalable data architectures, leading end-to-end data integration efforts, driving advanced analytics to empower data-driven decisions. As data architect, I have had the privilege of working with cutting-edge tools and methodologies like cloud technologies, different type of architectural patterns like microservices, event-driven architectures to solve real-world challenges. Today, I'll be discussing the design of distributed applications, emphasizing the importance of robust and scalable architectures. As we explore the architectural patterns, we'll identify common challenges and the best practices that can guide us in creating effective solutions. Understanding these elements is crucial for ensuring that our applications can handle growth and complexity while maintaining performance and reliability. Let's go into have a look at our today's agenda. Let's go to the next slide. Here's the agenda for today's presentation. We'll start with an introduction to the distributed applications, then the architectural patterns, the common challenges, the best practices and solutions. We'll try to cover a case study, and then we'll have the summary and question answer session at the end. A distributed system is a collection of independent computers that appear to the users of the system as a single coherent system. These computers or nodes work together, communicate over a network, and coordinate their activities to achieve a common goal by sharing resources, data, and tasks. The difference between we are accustomed with mainly centralized system. So the main difference between a distributed system and a centralized system is all data and computational resources are kept and controlled in a central place, such as a server in a centralized system. Applications that user connect to this hub in order to access and handle data. Although this configuration is easy to maintain and secure, if too many users access it simultaneously, or if the central server malfunctions, it could become a bottleneck. A distributed system, on the other hand, it disperses data and resources over several server locations, maybe frequently across various physical places. This gives better scalability and reliability, since the system can function in the event of a component failure. However, because of their numerous point of interactions, distributed systems can also be difficult to secure and administer as well. We have heard of various distributed systems. The terminology I think we're very much familiar of, like client server architecture, three-tier architecture, microservices architecture, event-driven architecture, service-oriented architecture. So these are the various common patterns we hear every day in our software world. So basically, the distributed applications they're designed for to improve performance, scalability, and reliability. So the examples like Netflix, Amazon, Spotify. So these applications show how they can handle vast amounts of data and user requests, showcasing their importance in modern technology. So that's how the distributed systems are so important in software architecture. This diagram briefly shows on a very high level how the nodes are connected to a server, and similarly there is another cluster which is connected over the network. So both of them working as a single coherent system. Let's move on to the next slide, which is about the key principles of designing distributed applications. All the major applications which run, let's say in a banking application, or maybe let's say email, for instance. The key principles which is followed while designing a distributed application, which is of very high importance, is scalability, availability and reliability, fault tolerance, maintainability, security. So these are the main principles which to consider when designing distributed applications. Like scalability ensures that the system can handle increased load by adding resources. Reliability ensures that the system can recover from failures. Fault tolerance ensures that the system can continue to operate even if there is some components like that fails. Performance basically ensures that the system can respond quickly to user requests. That's connected to scalability. So these are the major principles like we need to keep into consideration while designing distributed applications, which is of very high importance. Here in this slide, we'll basically listed the main architectural patterns. There are many patterns, but these the most commonly used and important ones I have listed here. So before we go there, we have heard a lot about architectural patterns. So what are architectural patterns? Architectural patterns are designed to provide solution to common design problems. In software design, we may have encountered many kinds of similar sort of problems. So the architectural designs which provide solution to those common designs are called architectural patterns. For distributed applications, for building distributed applications, like the major architectural patterns nowadays which are being followed in modern applications are microservices, event-driven architecture, CQRS, that is command and query responsibility segregation, then service mesh. Microservices we'll go into these ones in detail later on, but very briefly, microservices involve breaking down an application to very smaller components, which can be independently developed and deployed and scaled. Command query responsibility segregation is a design pattern which segregates read and write operations in a data store. This approach allows each model to be optimized independently. There are drawbacks to this model as well, but wherever possible, if you follow this in pattern, it definitely gives benefits. A service mesh is a dedicated infrastructure layer that manages communication between different microservices in a software application. So it provides tools and capabilities to handle tasks like load balancing, security, monitoring, ensuring efficient and secure interactions between those services. So that's service mesh. Now, in the next few slides, we'll go into a little bit detail of these architectures. We'll cover them as much as we can. Microservices architecture is a method of software development where an application is broken down into smaller, independent, and loosely coupled services. Each service is designed to fulfill a specific business function that can be developed, deployed, and maintained independently. This approach actually contrasts with the traditional monolithic architecture where all functionalities are tightly integrated into a single code base. The key principles around microservices pattern is independent development and deployment. So each component can be developed and deployed independently. So this helps in faster development cycles. Small focused teams, each team can be handled given a specific service, so they can work independently. Technology diversity, so each different microservice can be based on different technologies, which can leverage different skills of the teams. Fault isolation, if one microservice fails, then it doesn't affect the entire application. Definitely scalability. Scalability is a huge advantage in microservices application, that each component or each microservices can be allowed to scale independently. So you don't have to scale the whole application. So that's a huge benefit. How does microservices work? Basically, microservices communicate with each other through well-defined APIs, often using REST, event streaming, message brokers. So each service has its own database, ensuring data autonomy and reducing dependencies. This promotes flexibility, ease of development, and very easy maintenance. If you summarize the benefits, it's the modularity and decoupling, scalability, technology diversity, rapid deployment, continuous delivery. However, microservices comes with challenges as well. It's very complex to maintain, managing multiple microservices, very complex. Managing multiple microservices may require very careful orchestration and monitoring as well. Testing as a coherent model may be very difficult because of their interdependencies. Data consistency across microservices can also be challenging because these are all independent services. Network latency as well, because there's a lot of communications involved between those services, so it can lead to increase in latency. So this is very briefly covered where we covered the microservices architecture. Let's move on to the event-driven architecture in the next slide. In this slide, we'll briefly cover the event-driven architecture, aka EDA. Event-driven architecture software design pattern where system components basically communicate by generating, detecting, and responding to events. Events basically represent significant occurrences such as user actions or change in system state. In EDA, the components are decoupled, allowing them to operate independently. When an event occurs, a message is sent, triggering the appropriate response in other components. So again, in this architecture also, the key principles involved are decoupling. This is one of the major advantage of EDA architectures, it's decoupled relationship between front end and the back end components. This allows system to share information without knowing about each other. So producers can send events without knowing which consumer will receive them, and consumers can receive events without sending requests to producers. Asynchronous communication, it's basically EDA enables async communication where components operate independently and asynchronously in response to events. This allows for parallel processing, real-time responsiveness as well. Event handling, events are typically handled using a publish subscribe model, pub sub model. So components interested in certain types of events subscribe to them, while components that generate events publish them. So this model allows for flexible, scalable communication between the components. If we briefly touch upon what are the main components of EDA, it's the event source. Any component system that generate events such as sensors, databases, user interfaces, event broker or basically event bus. We may have heard it a lot many times. So it's an intermediary middleware that facilitates the communication of events between the components. So it handles the distribution, filtering, and routing of events. The publisher, a component that sends event to the event bus. Subscriber, the component that expresses interest in those specific type of events and subscribes to them. So subscribers always listen for events on the event bus and respond accordingly. Event handler is a piece of code or logic associated with the subscriber that specifies how to respond when a particular type of event is received. So benefits of EDA architecture, again, it's flexibility and agility. It allows to adapt easily to changing requirements. Scalability, it supports scalability by allowing components to operate independently. Systems can handle increased load or growing data sets by adding more components to the resources. Real-time responsiveness. So EDA, one of the major strengths of EDA is real-time processing, ensuring that events are handled as they occur. So that's why an EDA is used in many financial applications and IoT applications. Enhance modularity as well. Like any other pattern, EDA has got drawbacks as well. Definitely, it's a very complex system. Then consistency, maintaining the order of events and ensuring consistency across the system can be very complex. Debugging and tracing as well is very challenging compared to other architectures. Use cases of EDA is financial services, as I said, real-time processing of transactions, fraud detection, e-commerce, order placements, inventory updates. Internet of Things is a very good use case for the EDA architecture. Telecommunications, network monitoring, event-driven communication, network and components. Healthcare also, monitoring patient data, handling medical alerts, and those kind of things. This is very briefly, it's a vast topic, but we have covered it very briefly. What are the major components, their benefits, and the challenges. We'll move on to the next architecture, which is the CQRS pattern in the next slide. In this slide, we'll briefly cover the CQRS pattern, architecture pattern. So command and query responsibility segregation, CQRS, separates read and write operations optimizing both read and write operations. So in a traditional architecture where we have single data model is often associated with both read and write operations. So this approach is very straightforward and suited for basic crude applications operations. But in modern kind of applications, it poses a lot of challenges in their out performance. Some of the issues with that approach was data mismatch. The read and write representations of data often differ. Sometimes the fields that are required during updates might be unnecessary during read operations. lock contention, performance problems can have a negative, the traditional approach can have a negative effect on the performance because the load on the data store and the data access layer and the complex requests required to retrieve a lot of information, which impacts the read and write as well, like at the same time. Security challenges as well. It can be difficult to manage security when entities are subject to read and write operations. So this overlap can expose data in like unintended context. There are instances where it happened. So the solution is to these problems is a CQRS pattern, where we use the CQRS to separate the read and write operations, or basically commands, from the read operations or queries. So that's what like it says, command and queries. So commands update data, queries retrieve data. The CQRS pattern is in scenarios where that require a clear separation between commands and read. So it's not applicable in all scenarios, but wherever there is an opportunity, we should use it. So separating the read model and the write model simplifies the system design. Of course, like if the system design allows it to, that use case, if it is applicable to that use case. So it simplifies system design and implementation by addressing specific concerns for data writes and data reads. It increases clarity, scalability, performance, because those are now separated. So if you summarize the benefits of CQRS, it will be like independent scaling. So we can independently scale like the command and the query part separately. The schemas are now optimized. They're either write optimized or read optimized. So definitely there's a lot of increase like in performance, security, and also by separating read and writes, you can ensure that only the appropriate domain entities or operations have permission to perform write actions on the data, or maybe like on the read. Separation of concerns, then basically the writing of the queries can become a lot simpler. Then simpler queries, when you store a materialized view in the read database, the application can avoid like writing very complex. Anybody who has written a complicated query can understand, like the joins can extend and the query can be quite big. So if the design allows us to use this one, we should definitely use this one. In the next slide, we will go over briefly to the service mesh architecture. So in this slide, we'll briefly touch upon the service mesh architecture. So service mesh is a dedicated infrastructure layer that manages all the communication between the microservices in a software application. So it provides tools and capabilities to handle the tasks like load balancing, security, monitoring, ensuring efficient and secure interactions between those services. It has got two main components. One is the data plane, the other is control plane. So data plane is basically, it consists of sidecar proxies that handle the actual transfer of data between the services. They also implement like features like load balancing, service discovery, traffic routing. And control plane acts as a central management layer. It allows the administrator to define and configure services within the mesh, specifying parameters like the service endpoint, routing rules, load balancing policies, and security settings. This architecture has got benefits, namely service discovery, load balancing, traffic management, security, and monitoring and observability. It has got challenges as well. Like it's one of the main challenges, like it is very complex. It involves a lot of communication between the microservices, so there is a performance over it as well. There is operational overhead, like there's a lot of operational effort that goes into maintaining, deploying, configuring this architecture, and also that like the learning curve is very high. Designing a distributed application comes with several kind of challenges which we have to address. So namely the network latency, data inconsistency, service discovery complexity, then distribute transactions, and eventual consistency, the security. So all these are common challenges when we have to address while designing a distributed application. In this slide, we listed the various ways. We are very much aware of those. The tools or methodologies like for designing or increasing scalability, like horizontal scaling, which is like adding more nodes or computers. Vertical scaling is like adding more resources within a particular computer. So that's called vertical. Stateless and stateful. So we should always go for stateless designs. Load balancing. So there are tools like which are available, but which follow these kind of like round robin, list connections, go geo-based. So These are the tools. There are tools available which help us to achieve all these strategies, implement all these strategies for scalability. So we have to use them. In this slide, I have listed out the best practices which are normally followed while designing distributed applications. Designing for failure, it's a first and foremost fundamental principle or practice we should apply. We should design the application for failure. That means we assume that the application can fail in several ways, and we just design to avoid that using stateless components, CI/CD, using then the observability and monitoring tools. This has become a very important topic nowadays. Then practicing fault tolerance, security, load balancing, event-driven communication, so domain-driven design, then adopting chaos engineering. So these are the things which we should consider definitely into consideration when we design distributed applications. With this slide, we have come to near the end of the presentation. So here I've tried to summarize the key takeaways. So it all depends, when we talk about architectural patterns, it all depends on the right architecture choice. So we have to choose a pattern based on the fitment and the suitability for a particular use case. And obviously continuous refinement. This is a very important one. Even if there's an architecture which is implemented now, there can be enhancements or opportunities to use other patterns as well as you go along and as the application matures. So we have to always be open to that. So also challenges, there'll be challenges and you have to proactively deal with them, and we have to, as an architect, we have to anticipate the challenges for the next 3 to 4 years timeline and then plan accordingly. One thing which is just come up very strongly with these microservices, event driven, and the cloud deployments, investing in strong monitoring and observability tools. This is very critical. With this, we have come to the end of the presentation. So I have opened the floor for questions and answers. This is an opportunity to clarify any points we discussed today. Your insights and inquiries are extremely valuable for me, so please feel free to share your thoughts. You can also drop me an email or reach me individually later on as well. Thank you so much for your attention. Please feel free to ask any questions you may have, but I really appreciate your time and your patience today. Thank you so much. Have a great day.